So, last class I have discussed about different penetration tests, SPT and SCPT and DCPT, and then I have discussed different correlations by which you can determine the soil properties. So, today I will discuss about the pressure meter test. So, in the pressure meter test is another in situ test by which we can measure different soil properties by using the correlations. So, this is the pressure meter instrument, this is the instrument. So, it has a cylindrical probe and two gut cells. So, these gut cells are used to protect this probe within the borehole. So, here also we need the borehole, and here the pressure meter consists of a inflatable cylindrical probe. So, this is connected to a water reservoir. So, that means this probe can be expand when we apply the water pressure. So, we apply the water pressure, then this probe expands and we measure the volume change. So, this is the mechanism by which we can measure the properties. So, that means we apply the pressure, this probe expands. So, that means it expands and soil starts deform. So, then we measure this expansion and corresponding pressure, or you can say the pressure corresponding the expansion. So, that means the volume expansion we measure. So, this cylindrical probe inside we place it inside a borehole, then when you apply the pressure, the soil begins to deform and this probe volume increases. So, we measure basically pressure versus volume plot, or we do the pressure versus volume plot. We measure pressure and the volume change. So, volumetric deformation of the borehole is measured by noting the fall in water level in the water reservoir. That means, we measure the fall in water level, or basically the pressure and the volume. So, now this is the, as I mentioned, this is the pressure and the volume change. So, this is the plot that you will get from the test. So, that means, from this curve we can see this curve has three different zones. So, what are three zones? Initial volume of the probe, that is V0, that we can measure. Generally this V0 is 535 centimeter cube. So, that is known. So, V0 is known for us. So, this V0 is the starting point which is known, and initial pressure is say 0, and now we will start applying pressure. So, now this volume of the probe will increase from V0 to certain value, and pressure also increase. So, then we will get these three zones. So, initially we do not have these zones, we have to identify these zones. So, we have this graph. So, that means, once we get this graph, say suppose initial period we will get in some portion this pressure versus volume change is linear. So, we will identify these 2 points, the starting points and end points. The starting points where this linear zone starts, and the end points where this linear zone ends. So, that means, this linear behavior we have to identify these 2 points. So, we will identify these 2 points, and the corresponding volume is V0 plus small v0. That means, and corresponding pressure is P0. That means, to reach this point the volume change is small v0, and then the another point corresponding pressure is Pf, and the corresponding volume change is capital V0 plus small vf. So, that means, the volume change is small vf to reach this Pf. and this is the middle point which is V0 plus Vn. So, that means from to reach this first point, the volume expansion is V0, total volume is capital V0 plus small v0, and the second point the volume expansion is small Vf. Okay? So, the first zone is called the reloading zone, and the P0 represent in situ total horizontal stress. Why this zone is called reloading zone? Because when we construct the borehole, that means the pressure on the soil is released. So, the soil, some deformation of the soil will take place towards the borehole. Okay? Now, this is not the actual condition, because now the soil condition is been disturbed and some deformation of the soil takes place towards the borehole, inside the borehole, or you can say inside the borehole towards the borehole center. So, some soil deformation has been taken place. Now, once you apply the pressure and the probe start deform, then it will push that deformed soil to its original position. So, this first point, so at small v0 position, the soil will go to its original position. So, that is why it is this pressure P0 is called the in situ total horizontal stress, because that is the in situ condition of the soil. Okay, because now soil initially was disturbed, now we apply the pressure, now the probe expands. So, now it reaches its initial condition at this due to this V0 volume change at P0 pressure. So, this is called the reloading zone. Now, the next one is called the pseudo elastic zone, because here the pressure versus volume change relation or volume relation is linear. And third zone is called the plastic zone, and PL represent the limit pressure. This PL represent the limit pressure. Now, how I will get this PL? Now, PL I will get in two ways. That one is that if, because during this test I will get this plot, I will get this capital V0 plus small v0 value. Now, I have to continue the test up to 2 times capital V0 plus small v0, and there I will end the test. So, that corresponding pressure is the PL. Or and the second option is that suppose your instrument has some limits. So, you cannot go beyond some pressure or some volume change. So, there you have to stop your test. So, that may be the less than 2 times capital V0 plus small v0. Okay. So, now in such case how I will get the PL, because if my test ends before this 2 times capital V0 plus small 0, then how I will get that PL, because that time I have to get that PL by interpolating it. So, that means in the plot I will go identify the point corresponding to 2 times V0 plus capital V0 plus small v0, and then I extend this plot, extend this graph. So, that is interpolation, because I may not measure that value because of the limitation of the equipments, but I can interpolate this and I can go extend this curve up to that point, that means corresponding to this point, and then I can find out the PL value. So, if I can go up to that point, fine, I can measure, but most of the cases it is not possible to go up to that point. So, I have to finish the test before that point. So, I can interpolate that and I can locate the PL value, which is called the limit pressure. So, now from these values I will get the pressure meter modulus, which is the EP, that value I will get. This is the del P is the difference between P0 and PF, or PF and P0, and V is the Vf minus V0, small Vf minus small V0, that is del V, and then capital V0 I know, that is 335 centimeter cubes most of the cases. Mu is the Poisson ratio of the soil. So, I will get the pressure meter modulus EP. And as I mentioned, the PL limit pressure is usually obtained by, or this is extrapolating, because not the interpolation, it is extrapolation because it is outside the plot. So, it is extrapolation of the plot. So, it is not interpolation. So, correct this, it is extrapolation because I have to extend this, because your maybe the your test ends here. So, you have to extrapolate this plot. So, this is the extrapolation, because you have to extrapolate this plot up to this point, okay, but not direct measurement. So, again once you get this EP and PL, P0, PF, then again we have to use these values in correlations to get the soil properties. Again I will get the, I can get the undent shear strength or the cohesion, that expression is PL minus P0 by NP. So, PL I have already discussed, P0 also I have discussed, and this NP I will get by using this equation, and EP I will get by this equation, because EP I will get from this equation and I will put it here, but in that case that there also there will be a Cu and there also there will be a Cu. So, by trial and error I can get the Cu value. There is only one unknown, but the solution is very complicated. So, we can using the trial and error you will get the Cu if you use here, because here EP I will give the equation and the Cu I will get from this equation. Another case directly if you use the NP, which is vary from 5 to 12, average 8.5, then also I will get the Cu, and EP value I can also correlate with the SPTN. So, that also I can correlate for clay and the sand. The pre-consolidation pressure also PC I can get by using this correlation, half into PL, and pre-consolidation pressure also I can get. Now, the next test is the dilatometer test. So, dilatometer test also here borehole is not required. Here the instrument is pushed into the soil at a rate of 20 millimeter per second, and we test every 20 to 30 millimeter interval, and in pressure meter we use the water, but here the nitrogen tank is used, or nitrogen is used for inflating the membrane. Here also it is similar to pressure meter, but the difference is that here there will be a flexible steel membrane in this equipment, and that can where we have to use the nitrogen for inflating this membrane. So, this membrane will inflate and will get the deformation or the reading and the corresponding pressure we can measure. So, that means the previous similar to the pressure meter test, pressure meter also we measure the pressure and the volume change. Here also we will measure the expansion of this or inflation of the membrane and the pressure. So, it will give us the undent cohesion K0 value, that means the at rest coefficient of earth pressure at rest condition, over consolidation ratio, then CH coefficient of consolidation in horizontal direction, KH permeability in horizontal direction, and soil stiffness. It can identify the soil also. So, basically it has two major readings, actually it has three readings, but these two major readings we will use for the correlations. So, one reading is called the A reading and the next reading is called the B reading. So, in the A reading I will get the P0 and B reading I will get the P1. There is another reading C reading, there I will get the P2, but that we will not discuss here. So, here I will discuss about I will get the P0 by taking A reading and the P1 by taking the B reading. So, this A reading, B reading are different stages, okay, by which we are taking different readings. So, once we get these readings, we use these correlations for different types of soil. So, what is that? So, here first let me explain what is P0 and P1. So, as I mentioned, P0 is the contact stress, that is the pressure required to just begin to move the membrane. So, that means here P0 or the A reading, where we have to apply the stress, that initially when we apply the stress, immediately the movement of the membrane will not take place. We have to apply some reading such so that at that point the membrane will start deform. Okay? So, that the P0 is the pressure required just to begin the membrane to move. Okay? So, that is our A reading, and P1 is the expansion stress, that is the pressure required to move the center of the membrane by a amount of 1.1 millimeter into the soil. So, that means the P1 is the pressure that we will measure where the membrane will deform by 1.1 millimeter, the membrane center. The membrane center will deform by 1.1 millimeter into the soil, and U0 is the pore water pressure. So, it is clear what is P0 and P1. P0 is the pressure required to just begin to move the membrane, and P1 is the pressure required to move the center of the membrane by 1.1 millimeter into the soil. So, once I get this P0 and P1 and U0 I can measure, calculate, then I will get different properties. So, that means first one is the horizontal stress index. So, this is Kd. Kd is the P0 minus U0 divided by sigma V 0 bar. Sigma V 0 bar is the effective vertical overburden pressure. So, if I know the U0, if I know the sigma V0 bar and P0, from here I will get the Kd. Then I will get the dilatometer modulus, this is Ed. Ed is 34.7 P1 minus P0. So, once I get the Kd and Ed, then I will get these properties for the clay. Okay? So, those properties, this is mainly for clay. Those properties are K0. K0 is the coefficient of earth pressure at rest. Okay? So, this is the expression, correlation. Then undrained cohesion, this is the expression. Kd, again this is effective overburden pressure. Then over consolidation ratio is 0.5 into Kd to the power 1.56. So, you can see that for normally consolidated clay, Kd value is equal to 2. So, if your soil has a Kd value is 2, then we can say this is a normally consolidated soil. Okay? And if it is more than 2, then it will be a over consolidated soil. So, for normally consolidated soil, this is the correlation. So, if I get the undrained cohesion for the normally consolidated soil by using these correlation, then I can use this correlation to get the undrained cohesion for over consolidated clay also. So, that is the normally consolidated clay into 0.5 Kd to the power 1.25. This is into. Okay? So, this is actually, this value is, this is into. Okay? So, then I will get the elastic modulus by using these expressions also. Mu is the Poisson ratio, Ed I will get from here. So, these correlations are for the clay. Okay, that means the K0, Cu, OCR, E, and then Cu I can get for, this is for a normally consolidated clay, for over consolidated clay also you can get. So, this Cu depending upon Kd value, I can get whether it is a over consolidated soil or normally consolidated soil. So, if it is a normally consolidated clay, directly I can use these expression, and over consolidated soil I have to use these expression. Now, next one is to determine the horizontal coefficient of consolidation and the permeability of the soil, and these correlations is also for clay. So, previous correlations are also for clay, these correlations are also for clay. So, I will get the horizontal coefficient of consolidation. So, that is CH. So, that is equal to 7 centimeter square by T flex. So, the T can be second or minute. So, that means the CH will be either centimeter square by second or centimeter square by minute, depending upon how T you are putting T flex value. Now, what is T flex? So, here as I mentioned that during this test we are taking two readings, one is your A reading, another is your B reading. A reading will give you P0 and B reading will give you P1. So, here we will go for the A reading only. So, this is the A reading, that is why. So, this is the pressure that you will give during the A reading. So, that A reading will take, and we will off this P reading, I mean B reading will not take. We will keep this instrument under A reading condition and we will take the reading at different time interval. Clear? So, that means we will keep the instrument under A reading condition, and then at this condition we will keep on taking this reading with different time interval. So, this is the different time intervals. You can see this 1 day, 1 week, and we can take this 1 minute, then 5 minutes, then 10 minutes. So, different time intervals we will take the reading, and so we will plot these readings with time. This is x axis is time in minute and y axis is the A reading. So, with time, and then we will identify there will be a change in curvature in the curve. You can see. So, this is the curvature and then there is a change, okay? Change in curvature. So, this is one curve and then it is the change. So, we have to identify that point, okay? So, that point and the corresponding time will give me the T flex. So, this is called point of counterflexure. So, this is called point of counterflexure and this is small T flex. So, this point of counterflexure we have to identify by plotting this A reading and the time. Okay. So, this is the point of counterflexure and that means where your curvature changes. So, identify that point and the corresponding time will give me the T flex. So, you put this and you will get the horizontal coefficient of consolidation. Now, the horizontal coefficient of permeability I will get by using this expression. This is CH I will get from this expression, then MH. MH is the K0 and M dmt. So, K0 it is the coefficient of earth pressure at rest that I will get by using this expression, the K0 by using this expression K0 I will get, then CH also I will get from this expression. This is gamma W is unit weight of water, and M dmt I will explain what is M dmt. Now, for this M dmt which is drain constraint modulus, okay, of the soil, the constraint modulus is generally 1 by MB, MB is the coefficient of volume change. So, and this M dmt will get Rm into Ed. Ed I will get from this expression, Ed I will get from this expression, and how I will get the Rm. So, RM I will get by using these conditions. So, to get the RM we have to identify the ID, which is called material index. So, ID I will get by using this expression P1 minus P0 divided by P0 minus U0. So, P1, P0, U0 I have already explained. So, this ID I have to calculate material index. This based on this ID I can identify the soil type also. If your ID is less than 0.6 and greater than 0.1, then it is clay. If it is less than 1.8 and greater than 0.6, then it is silt. If it is within 1.8 to 10, then it is sand. Okay. So, here in previous expression, as I mentioned, it is valid for ID less than 1.2. So, it is mostly clay, okay, because clay is 0.6. Some silt is also there because it is less than 1.2, but it is mostly clay. But if these expressions, if we have to use if ID is 1 point greater than 1.8, then only those expressions are valid for sand. Those expressions are valid for sand if your ID is greater than 1.8, because that is then only your soil is sand, otherwise soil is not sand. So, okay, so now ID I can, by these conditions ID I can calculate for clay, ID I can calculate for silt, I can calculate for sand also. Okay, so now if your ID is less than equal to 0.6, that means it is clay, then RM will be this equation. So, I will get the RM by for the clay for this equation, this is the KD, this is log 10 RM, and I will put RM here and I know the ED, I will get the DMT, and that DMT I will put it here, I will know the K0, I will know the MH, and that MH I will put it here, I will get the KH, the horizontal coefficient of permeability. Is it clear? Okay. Now, I will go for the sand part. So, previous correlations are valid for the clay. These correlations are valid for the clay, mainly clay. Now, I go for the sand part. Now, if your ID is greater than 3, then which is basically sand, then RM is these can be obtained by using these expression. If ID is in between 0.6 to 3, then RM will be obtained by using these expression. Okay. Now, here what is RM 0? RM 0 can be obtained by using these expression. Now I can obtain the RM for clay, silt and sand, okay, depending upon ID value. Now, note that if your KD is greater than 10, then you have to use these equation, because this is the based on the ID, but these are the two special cases. Suppose if your KD is greater than 10, then directly you use RM is can be obtained by using these expression. Then ID classification or ID different types of ID are not required. So, if your KD is 10, so that means initially you check what is your KD value. If your KD is greater than 10, directly you use this RM expression. Now, if your KD is less than 10, then you based on different ID you calculate the RM. Clear? If your KD is greater than 10, using this expression, and if your KD is less than 10, then based on different ID value you will get the different RM value. And another condition is that if by any chance by above expression is giving the RM less than 0.85, then you take RM is equal to 0.85. Your RM cannot be less than 0.85. RM you have to take 0.85 or more. So, now for it is very difficult to identify the whether sand is normally consolidated state or the over consolidated state, because in clay you can test the oedometer, you can do the oedometer test, and you can identify the what is the PC and whether you can identify the soil is because you can identify the PC, which is very important to know to understand whether soil is in over consolidated state or the normally consolidated state. But in the sand, doing oedometer test is difficult because of its disturbance. So here by the dilatometer test, approximately we can identify whether sand is in over consolidation or consolidated state or normally consolidated state. How we can do that? Because once we get the RM for sand also, then also we will multiply with ED, I will get the MDMT. So then that MDMT we divide it with the QC, that means the cone resistance. Cone resistance, that means the static cone penetration test, I will get that value. I have already discussed the static cone penetration test. So that from the static cone penetration test, I will get the QC, and that MDMT you divide the QC. Now for normally consolidated sand, this MDMT divided by QC is within 5 to 10, and for over consolidated sand, this value is 12 to 24. So we have to, based on the ID value, we have to calculate the RM, and that RM we will put it here, we will get the MDMT, and then we will divide it with the QC, then we will get the, we can identify based on this range whether soil is normally consolidated state or over consolidated state. Okay? So this way we can identify that. So now the next one is the, for the sand also we can calculate the K0 by using this expression. This QC, this is the cone resistance that I will get the static cone penetration test. That is sigma V0 bar, that means effective overburden pressure. Now I can get the phi also by using this expression. I can get the phi by using this curve also, because I can get the K0 by using this equation. If I know the QC and effective overburden pressure, then I can get the phi value also for the soil. So either I can use this chart or I can use the expression to get the phi value of the soil. So here next class I will discuss the few more in situ test by which we can determine the soil properties. Thank you.